Hi, welcome to our presentation on diverse sampling strategies for active learning on satellite imagery. Our mentor on this project works for a NASA subsidiary called SpaceML. The long-term goal of SpaceML is to accurately identify hurricanes and other natural disasters using data from space imagery. The problem is that labeling data can be very expensive due to the requirement that the human labeler has a very specific skill set in reading space imagery. Thus, we choose to use active learning in this low data context. Here are the iterative steps to our active learning pipeline. First, we train a base model. Then, we perform uncertainty sampling to attain uncertainty scores for each unlabeled data point. Next, we choose a diversity sampling strategy to select which data point we want labeled. These data points are then labeled by a human specialist. Our model is then retrained on all of the labeled data points, and we return to step 1. So how do we even calculate uncertainty scores for data points if we don't have their labels? Well, we can train a ResNet-18 model and calculate class probability values. We can then observe the probability distribution to calculate an uncertainty score. More specifically, we use 3 different methods for calculating our uncertainty scores. Least confidence, which is 1 minus the highest probability, margin-based, which is the second highest logit minus the highest logit, and entropy, which is a standard measure of uncertainty with this formula. Now that we have uncertainty scores, we can use the greedy strategy to select data points that we want labeled. Simply sort the data points by uncertainties and choose the top n data points. So the problem with this strategy is that the top n data points with the highest uncertainties will be uncertain in similar ways. As an example, they might give you data points that lie on the same difficult decision boundary. Ideally, we want more diversity in our sampling strategy. We can achieve this by using the help of embeddings. We utilize the pre-classification layer of our ResNet-18 model. The first of our diversity sampling strategies is clustering-based sampling, where we first cluster the embeddings. We then count the number of data points in each cluster. Lastly, within each cluster, we select the data points with the highest uncertainties. The number of data points we choose from each cluster is proportional to the number of data points within that cluster. In this example, we were told to pick 9 data points, and we will select the top 2 from green, the top 3 from blue, and the top 4 from red. The next diversity sampling strategy is a novel strategy which we call iterative proximity-based sampling. First, we choose the point with the highest uncertainty. Then, we set the centroid to that point. We can then calculate the distances between the centroid and all other points as shown on the lines of this diagram. We then linearly transform the distances to be within the range -0.3 and 0.3. Next, we calculate the total score for each data point as a sum of the uncertainty score and the distance score. We can then select the point with the highest total score. Next, we set the new centroid as the mean of all previously selected points. This centroid is then used on the next iteration to calculate the Euclidean distances.
We take these sampling techniques and run experiments on 2 different datasets. The first is a commonly known CIFAR10 dataset that has 10 classes with 60,000 samples. The other is a considerably smaller dataset from UC Merced, which has 21 classes of satellite imagery. We used a ResNet-18 as our model of choice to conduct these experiments, taking into consideration both efficiency and performance. For the CIFAR10 results, we can clearly see that both least confidence and margin outperform random sampling significantly, while entropy does not. We also observe least confidence and margin nearing the full dataset accuracy with only 40% of the total labeled data. The same can be seen for our UC Merced data, illustrating the generalizability of these active learning approaches. Given our results, we see a clear benefit to using least confidence and margin-based uncertainty sampling methods, cutting down the cost of labeling by over 50%. As for the diversity sampling, we observed mixed results. One possible reason for this is the similarity of our classes in a dataset like CIFAR, for example, trucks and automobiles, or dogs and horses, which may result in the diversity methods grouping them in the same cluster. In conclusion, active learning has shown to be an effective approach to reach similar performance with significantly less labeled data using different uncertainty and diversity techniques. Thank you for your time.